On November 9, something unusual caught the attention of astronomers around the world. New images of an interstellar object known as 3I Atlas were released, and they immediately raised more questions than answers. The object appeared as a sharp, bright point of light. There was no visible tail, no dust cloud, and no sign of gas being released, features that are normally expected when such objects pass close to the Sun. Even more puzzling, its appearance had not changed since earlier observations months before. For something exposed to intense solar heat, this lack of change seemed highly unusual. As scientists examined its motion, they noticed something even stranger. Instead of slowing down as expected, the object showed a slight but measurable acceleration. Though small in magnitude, this shift was significant enough to stand out from predicted orbital models. Normally, such behavior in comets is explained by outgassing, jets of vapor pushing the object like a natural thruster. But in this case, there was no visible evidence of that process. This created a dilemma. If the object were releasing material, telescopes should easily detect it. But observations showed nothing. No glow, no expanding cloud, just a steady, compact point of light. Comparisons with known comets made the difference even clearer. Typical comets display long, flowing tails shaped by solar radiation. 3I Atlas, however, remained unchanged, calm, contained, and almost featureless. Some researchers began exploring alternative explanations. Could it be an unusual type of object? A fragment with unique composition? Or something not yet fully understood in current models of physics? While a few speculative ideas emerged, including artificial origins, most scientists remain cautious. Extraordinary claims require strong evidence, and so far, the data, while intriguing, remains incomplete. Further analysis revealed additional oddities. Its path through the solar system appeared unusually well aligned with planetary orbits. Its brightness changed in ways that didn't match typical patterns. And its color leaned toward a deeper blue tone, which is uncommon but not entirely impossible under certain conditions. Spectroscopic data suggested a composition that differed from standard icy bodies. Instead of being rich in volatile materials like water ice, it appeared relatively dry. This raised questions about its origin, whether it formed in a different type of environment or underwent processes that altered its surface over time. As more observations came in, the mystery only deepened. Some scientists proposed that unknown natural mechanisms could be responsible. Others argued that gaps in current models might explain the behavior. But no single explanation has yet been confirmed. The object's closest approach to Earth provided an important opportunity for further study. Telescopes around the world focused on it, collecting as much data as possible. Researchers hoped that clearer measurements would either confirm known theories or point toward new ones. For now, 3I Atlas remains an open question. It does not fit neatly into existing categories, but that does not necessarily mean it is something artificial or extraordinary. Science often advances through such anomalies, moments where observations challenge expectations and lead to deeper understanding. What makes this object compelling is not just its behavior, but what it represents, a reminder that space still holds many unknowns. Each new discovery pushes the boundaries of what we know and invites us to look closer, question assumptions, and refine our theories. Whether 3I Atlas turns out to be a rare natural object or something that forces a shift in current understanding, it has already achieved something important. It has captured attention and sparked curiosity. As observations continued, the story of 3I Atlas became less about a single anomaly and more about a growing collection of unanswered questions. Data from multiple observatories began to paint a more detailed picture. The object's brightness remained unusually stable, even as its distance from the Sun changed. Normally, objects like comets brighten dramatically when heated and fade as they move away. But here, the pattern didn't follow expectations. The consistency suggested either an extremely uniform surface, or a process not yet understood. Its trajectory also drew attention. When scientists mapped its path precisely, they found it passed through regions of the solar system in a way that seemed almost too orderly. While this could still be coincidence, the alignment added another layer to an already complex mystery. Meanwhile, spectroscopic analysis, used to study the light coming from the object, continued to challenge assumptions. The signals did not match the typical fingerprints of ice-rich bodies. Instead, they hinted at a composition with more metallic or rocky characteristics. This didn't make it artificial, but it did make it unusual compared to most interstellar visitors detected so far. Another point of debate was temperature. Some measurements suggested higher than expected energy levels for an object at that distance. Under normal circumstances, such heat would lead to visible changes, melting, fragmentation, or gas release. Yet none of these were clearly observed. Because of this, scientists began exploring less conventional natural explanations. One idea involved a surface covered in highly reflective material, allowing it to resist heating more effectively. Another possibility was that it could be a dense fragment from a larger body, with properties unlike typical comets. There were even discussions about whether interactions with solar radiation could produce subtle forces without visible outgassing. Despite all this, no single explanation fully accounts for every observation. It's important to understand that in astronomy, incomplete data is common, especially with objects passing through the solar system at high speed. Observations depend on timing, distance, and available instruments. What seems mysterious today can often become clear with better measurements tomorrow. Still, 3I Atlas stands out. Not because it proves anything extraordinary, but because it resists easy classification. Moments like this are valuable. They test the limits of current knowledge and encourage scientists to refine models or consider new ideas. History shows that many breakthroughs began with objects or phenomena that didn't behave as expected. For now, researchers continue to monitor the object as it moves farther away. Each new data point helps narrow the possibilities. Over time, patterns may emerge that reveal a more complete explanation. Until then, 3I Atlas remains exactly what science often encounters at its edges, something not yet fully understood, waiting for better data, better tools, and better questions. One area of intense study was the object's motion over time. When plotted across weeks and months, its acceleration appeared smooth and continuous rather than chaotic. Natural forces, like outgassing or gravitational nudges, usually create irregularities. But this motion showed a kind of consistency that made it easier to model mathematically, yet harder to explain physically. At the same time, teams compared it with previous interstellar visitors, particularly Oumuamua and 2I Borisov. Both objects had their own mysteries, but they still behaved broadly within the limits of known physics. 3I Atlas, however, seemed to push further beyond those boundaries. Another interesting development came from polarization studies, how light waves aligned after reflecting off the object's surface. The readings suggested a highly uniform structure. In nature, surfaces tend to be irregular, scattering light in complex ways. But here, the signal hinted at an unusual level of consistency, though still not enough to draw firm conclusions.